For more than 100 years, visionaries have dreamed of humans living and working in a permanent outpost in space. The space age began in earnest when Wernher von Braun and his fellow German rocket scientists came to the United States after World War II. Von Braun was a visionary who hoped to use German rocket advancements for space exploration. A special section in a 1952 issue of Collier's magazine featured von Braun's vision for space developments, which was highlighted by a space station. He proposed a wheel-shaped space station with 3 decks, 250 feet wide, circling the Earth every 90 minutes in a polar orbit. Von Braun saw a space station as an inducement for world peace. He said, with a space station, we can not only preserve the peace, but we can take a long step toward uniting mankind. The first step in turning concept into reality was taken in 1971 when the Russians launched Salyut 1, the first manned space station. Since then, a total of 8 space stations have orbited the Earth, 1 U.S. and 7 Russian stations. The Russians have orbited Salyut and Mir space stations continuously since 1971. During that time, the cosmonauts have set several duration records aboard their space stations. The most recent was in March 1995 when Valery Polyakov returned to Earth after 438 days, which broke the record for the longest single spaceflight in history. Overall, Russians have accumulated about 27 man-years, with 76 total launches. The first U.S. space station, called Skylab, was launched in 1973 using a modified Saturn rocket, similar to those that took astronauts to the moon during 9 Apollo missions. The rocket's 3rd stage was outfitted as an orbital workshop and living quarters for 3 crew members. Overall, 9 astronauts on 3 crews lived and worked in this station for a total of 168 days. During their time in orbit, Skylab astronauts conducted more than 100 experiments involving physics, Earth observation, space science, material processing, and life sciences research. They also conducted sophisticated medical tests to understand the body's adaptation to space, and were able to do unique research on microgravity's influence on fluid and material properties. Skylab offered more proof that humans could live and work in space for extended periods. Skylab also demonstrated the value of human involvement in construction and maintenance of space vehicles on orbit. Since it was not equipped for its own reboost, Skylab's orbit gradually decayed over the 6 years it flew. In 1979, it re-entered Earth's atmosphere and was destroyed. Today, Skylab studies are the baseline for ongoing microgravity investigations on board the Space Shuttle, and soon the International Space Station. When Space Shuttle Columbia lifted off the pad for the first time in April 1981, plans for a space station were dusted off. In January 1984, President Reagan directed NASA to develop a permanently staffed space station within a decade. Reagan named this station Freedom and stressed that the station would seek international participation. Over its 9-year history, Freedom went through 6 major redesigns, largely in response to changing funding levels. In September 1988, Space Station became an international endeavor with the signing of official agreements between member nations of the European Space Agency, Japan, Canada, and the United States. European Space Agency countries participating in this program include Belgium, Denmark, France, Italy, Germany, the Netherlands, Norway, Spain, and the United Kingdom. In March 1993, President Clinton asked NASA to redesign the space station and provide options that would develop a more efficient and effective program capable of greater return on investment. This redesign effort was required to reduce overall costs while achieving long-duration research goals, streamline management organization, use Freedom systems as much as possible, and encourage additional international participation. Today, those requirements are being accomplished. The station has been redesigned, and the program has been restructured. It combines the elements of Freedom, simplifies many subsystems, and integrates Russia as a new international partner. Russia's experience with long-duration flights and space station operations will result in the final station assembly being completed 13 months earlier for a cost savings of $2 billion. In addition, a permanent crew presence will be established more than 5 years sooner than previously anticipated. This earlier on-orbit research capability translates into a significant increase in scientific returns. The redesign effort has also resulted in the creation of a single management team, which replaces the previous dispersed management approach. NASA's Station Program Office and the single prime contractor responsible for Station are co-located at Johnson Space Center, the host center for Space Station. A different management concept called integrated product teams has been implemented. These teams are responsible for a product. They are empowered to make most decisions affecting their product's suitability, quality, and cost. This concept forces the decision-making process down to the people with the best technical understanding of the product. It involves designers, operations, and people on the manufacturing line, all working together. Integrated product teams are concurrent engineering. It's a new way of doing business, and it's working. Redesigns and view-graph engineering are history. In less than 3 years, crews from 13 different nations will begin permanent operations on the International Space Station. 3 phases will be used to build this station. During Phase 1, the U.S. Space Shuttle will travel to the present Mir station. Joint activities will include dockings, crew exchanges, and spacewalks. Actual Phase 1 cooperative activities with Russia began in February last year, when Sergei Krikalev became the first Russian cosmonaut to fly as a shuttle crew member on STS-60. The next step, docking a shuttle to the Mir, was successfully completed during the STS-71 mission.
Houston, Atlantis, we have capture.
Copy, capture.
With the capture initiated between Atlantis and Mir, 20 years after Apollo-Soyuz, a U.S. spacecraft and a Russian spacecraft are once again joined in orbit.
It's a great feeling to be here. It's a massive team effort. Many people have pulled together to make this happen. We're lucky and we're honored and privileged to be part of this. It's great to be back joined in orbit again. Houston, we have separation.
Concur, separation.
Six more Shuttle-to-Mir missions are planned. These joint flights offer the opportunity to test station hardware, assembly procedures, and operational tasks which will reduce station's assembly risk. It also provides an opportunity to do long-duration research. The core space station assembly will start in 1997 with Phase 2. The mission for this phase is to provide initial capability for science operations in the U.S. laboratory. At this point, the station will be operated by a 3-member international crew. The first element of the International Space Station will be a module called the Functional Cargo Block. This 20-ton self-contained spacecraft is being built by Russia under contract to the U.S. and will be launched in November 1997 on a Russian Proton booster from the Baikonur Cosmodrome. It will serve as the foundation and key building block for subsequent space station elements. The first shuttle flight will follow about a month behind the Functional Cargo Block launch. An orbiter will carry up the first station node, which provides the structural and utility support for a number of other elements. The shuttle will fly to a 190 nautical mile orbit and rendezvous with the cargo block. The shuttle's robotic arm will grapple the cargo block module and dock it to the mating adapter on top of the node. Then the shuttle will release the attached cargo block node assembly, back away, and deorbit to get ready for another assembly mission. In the spring of 1998, a Russian cooperative flight will bring the service module into space. This provides the living quarters for the crew and additional power, computers, communications, and life support. Shuttle flights will continue at the rate of about 7 per year as the station is built using a sequence which coordinates Russian, U.S., and international partner launches. Flight 3A puts up a piece of truss assembly for a large solar array which will follow. The next shuttle flight will carry the first of 4 U.S. solar arrays, each with a capacity of about 19 kilowatts. The U.S. laboratory is the first research module to be activated on the station. Shuttle astronauts will use the robotic arm and spacewalks to position the module on the front of the node. This first laboratory will be an expansive, well-equipped module which will have significantly more capability than any previous research facility flown in space. It will have extensive accommodations for 13 research racks, each of which is about the size of a large refrigerator. Phase 2 ends with the outfitting and initial operation of the U.S. laboratory and airlock. However, the construction of the station continues at a rapid pace. Phase 3 completes the International Space Station as construction finishes in June of 2002. The assembled station supports a complex of 7 laboratories, including 2 U.S., 3 Russian, 1 European, and 1 Japanese. The station will be orbiting at about 220 nautical miles above Earth. A 6-person crew will be aboard for 90 to 180-day research increments. With its orbit inclined 51.6 degrees to the equator, the station will fly over about 85% of the world's surface. This provides an important capability for climatic and atmospheric research, oceanography, and remote sensing for geology, land use, and other activities. For at least 10 years, the space station will serve as a world-class orbiting research center. Research on present-day shuttle missions is aimed at maximizing the productivity of experiments planned for the station. These experiments include fundamental fluid physics, protein crystal growth, exercise countermeasures, microbiology, and extensive life sciences research. The space station is the largest international science project ever. Currently, 14,000 U.S. contractors and government personnel are working on producing the station. Almost 300 tons of U.S. hardware is being developed, tested, and readied for assembly in space. Our 12 international partners are working on similar activities in their own countries. The space station program is now a key element in bringing together the industrial, aerospace, and research activities of diverse groups around the world. We are building the station for the benefit of all people and nations. The dream of humans living and working together in a permanent outpost in space is well on its way to becoming a reality.
Picking up some dust. Contact light. Okay, engine stop.